Hello, welcome. What I'm going to do today is calculate the magnetic force due to two currents of wire. So it's going to be a little more challenging because what we have is a loop of wire. So basically, we're going to be figuring out the magnetic force for each of these segments. And once we do that, we'll figure out the net force on the loop, because that basically means find all the forces and sum them up. So sum of forces. So what we're going to use is the equation that I introduced in class toward the end, which is essentially K prime, I1, I2, the length of the wire, all over D. So just a quick recap of this. This all stems from the fact that we can get a magnetic force from a current carrying wire as I, B, and L. But where this extra stuff comes from is the B comes from the wire. So that's the K prime I over D. So that's basically where this extra I comes from. So that's why we have two I's here, where this is the length of the wire and this is the distance between the wire. So this is, of course, for two wires, where this is single wire. Like that. So now let's figure out the forces acting on all this. So what I'm going to do is break this down into segments, because all of these will feel a force. All of these segments. Now they're going to feel a different force for two reasons. One, the direction of the current changes, right? It goes all different directions. So because it changes all different directions, we're actually going to get different directions of force. So we're going to be using the right-hand rule as well to figure out the direction of force. Actually the right-hand rule for this, but it applies for this as well. So what I'm first going to do is figure out, because in order for this to even feel a force, it has to be in the presence of a magnetic field. So it's actually this wire that's generating the magnetic field. So I know this is, I'm going to be using the right-hand rule, but this video is mirroring everything I do, so don't pay attention to what I'm doing, but I'll talk it out. So what I'm doing is taking my right hand, and I'm going to line it up with this wire first to figure out my magnetic field. So if I do that, my thumb will point to the right, and my hands will curl around this. So I will do that, thumb to the right, and I curl around this. So when I do, I have it going into the page in my loop of wire and then out of the page at the top of the wire. So I have out of the page at the top of the wire and into the page here. Which means basically this whole section, the magnetic field, is into the page. So I'm just going to write only a few X's here. Okay, now that we have the magnetic field and the direction of the current, that's going to help us find the direction of our force. So we're going to go through and calculate each section of this wire. And again, the reason why we do that is because the direction of the current changes. So let's do section 1. So the force in section 1 is going to be K prime, which I'll write it out, 2 times 10 to negative 7. And here's our units for K prime. I'll call this I1. Now they happen to be the same value, so this doesn't really matter, but let's just do it anyway. So I1 is going to be the 2.5 amps. I2, I'll call this one, this whole loop of wire, which happens to be 2.5 amps. Now when it comes to the length of the wire, that is the length of the wire that's present in the magnetic field. So it's not this one, it's this wire, because this is inside the magnetic field. So the length of section 1 is 10 centimeters, so that's where this number goes. Now the distance between these two wires in this case is 3 centimeters. So we're going to go ahead and convert that into meters, but that is the setup for a force. So it's not too bad. Actually, my calculator, oh, it's right there. Okay. So let's calculate this out. Okay, so naturally we're getting small numbers because this happens to be pretty small. So what I get when I calculate this, I'm just double checking my calculations, they look okay, is 4 point, I'm going to round, 2 times 10 to negative 6, and this will be in newtons like that. So that is the force. Now we need to know the direction because we need to know the net force. So right-hand rule. Alright, what I'm actually going to do, because you can't see my right hand, it's not going to, it's kind of tough like this, so I'm going to just draw out my right hand the way it would look, right? So my fingers would point along the direction of the current, my palm would face in. So if I do that with my right hand, you would see my fingers go along the current, my palm is in, and when I do that, my thumb goes up, and that's the direction of the force. So my force is up at section 1. So that's basically, I'm going to do this 3 more times. So here we go. At location number 2, we have the following setup. We have K prime, which is 2 times 10 to negative 7 meters Tesla over amps. I have current 1, current 2. Now the length of the wire, in this case, is our 5 centimeters. Converted right into meters. Now, this is the interesting part, right? Notice that, I mean, this is changing distance, right? It goes from 3 to over here, which is 5. So when we calculate that, so what we could do with that is, right now I'm just going to put D here because that's actually kind of difficult. So I actually see the fact that these two forces are going to do something interesting. Watch what happens when I use the right-hand rule here. So if I do that, my fingers will point down. And, oops, my fingers will point down, which means my thumb goes this way. So this is the way my right-hand rule looks over here. My thumb goes this way. So my force will be in this direction here, even with the crazy D, because this is technically a changing D. If I do the same thing on the other side, my fingers line up with the current, my palm is into the page, so my hand over here looks like, oops, looks like this. My thumb actually goes this way with my fingers going up like this. So my force on segment 4 here is actually this way. Now since all of this is identical, in other words, that my force 2 is going to be equal to my force 4. Or in other words, they're going to cancel. So regardless of what these values are, it doesn't matter because I have one pulling this way, one pulling that way with the same information. They'll cancel out. So so basically, the moral of the story is this is actually difficult to solve because of the changing distance here. So we're not going to even worry with that by finding that, or saying pretty much that these two forces cancel out. And the way I did that is using the right-hand rule. So what's going to happen is, technically just segment 3 is what we're going to care about. And if you look at segment 3, we'll just use the right-hand rule here. So if I point my fingers in the direction of the current, my fingers will go this way, my thumb goes down. So my force for segment 3 is down. and up, so you can see that. So what that means, my force 3 is going to be K prime times current 1, which we said was the top one, current 2, which happens to be the same, the length of the wire, so you can see the length of the wire is still 10 centimeters, so this is the same, all divided by the distance. Now in this case the distance is constant, it's going to be 3 plus 5, which makes it 8. Let's go ahead and do that. Okay, so what we get when we calculate this out is 1.56 times 10 to the negative 6, and this is in newtons. And then we already used the right-hand rule here, so that's down. So if I were to draw a free body diagram of this, just to kind of get an idea, I would have a up force of 4.2. I have a down force of 1.56. And I have equal and opposite forces right and left, like this, which I'll just label as F right now, because we didn't actually cancel it, but we know that if you pull one way with the one amount in the same way in the opposite direction, they're going to cancel. So if you notice, we could get the net force because we have to basically take some of the down and cancel out some of the up. So in other words, to find the net force, I'm going to do the force up minus force down. That'll be the net force. So with that said, it's 4.2 negative 6 newtons minus 1.56 times 10 to the negative 6 newtons, like that. So let's calculate that out. 4.2 minus 1.56. I get 2.64 times 10 to negative negative 6 newtons. And the leftover, so this will be up, since it's positive. But I solved this out. So what does this mean? This means that this whole wire will actually, in the presence of this magnetic field, will move up with that force that we calculated down there. So that's how you can use this equation right here to figure out the net force on a loop of wire like this. So if you have any questions about it, just let me know, and I'll be happy to answer them.